Hi everybody, and welcome to section 2.5, where we're looking at some of the physical applications of integrals. Now, a little disclaimer here, I am not a physicist. I certainly know some physics, and enough to teach this section, but it's not my area of expertise, and so I'll probably have fewer insightful things to say about some of this material. And I won't be as kind of well versed in some of the history and or some of all of the purposes of doing some of these things. Certainly, they seem practical, and that's kind of the purpose of this section. It's not to make you an expert at doing a lot of these physics problems, but rather to convince you that integrals are physically meaningful and have some important purposes, as well as to get you comfortable with the notion of using them in some of these applications where where some quantity is changing over the movement of some object or something, and in order to get some other meaningful quantity, we have to do an integral in order to learn something interesting about the situation. So with that said, let's take a look at some of these physical problems and how we can solve them using integrals. So one problem in physics is this question of how do you compute the mass of a very thin fiber? So certainly if you've got some fiber and it probably doesn't weigh very much. Especially if it's very thin, even on the level of where its thickness can be measured on like an atomic scale or something like that. In that case, you probably can't just pick up your fiber and put it on your kitchen scale and figure out how much it weighs. We need to do some other work in order to figure it out. Your average kitchen scale isn't going to be able to detect the difference between, say, your fiber and the dust that's sitting on it. Instead, what we need to do is we need some other kind of techniques. And fortunately, we have tools like scanning electron microscopes, which allow us to compute this thing called linear density. So this is going to be the goal, is we're going to work with this linear density function. So what is linear density? Well, the idea is that if you have constant linear density, let's call that linear density the Greek letter rho, is going to imply that the mass is equal to rho times the length of the wire, or the length of the fiber. So in other words, what we can really do is we can think about rho, or this linear density thing, as being equal to the mass divided by the length. But certainly, it's not always going to be the case that a fiber has constant density. Sometimes it will be less dense on one end, sometimes it will be more dense on another end, sometimes it will have different density in the middle. And so what we want to do is we want to have a way of taking a linear density function, which varies depending on where you are in the fiber, and then turning it into the mass of the fiber itself. So but linear density may vary. So we want to know how to deal with this. And the idea is that we're going to take, if we have some, we're going to put our wire on the x-axis. So we'll draw the x-axis here. And we're going to take our fiber, and we're going to probably place it with the left end at the origin, but it's not really important. Maybe we could call the left endpoint, as usual, A, and the right endpoint, as usual, B. So we've put our fiber here, and we want to, maybe we know its linear density function, so we'll call that rho of x, being a function that spits out the linear density at any given point on the fiber. And with this, what we want to do is we want to split up the fiber into a bunch of very small pieces. So we're going to partition the interval from A to B, and we're going to look at the xth piece, with the distance here as usual being dx, And if I want to compute the mass of this little blue piece that I've drawn here, then what I can say is that the mass is the linear density times the length. So since we've looked at a very small component of the fiber here, we can assume that the linear density is approximately constant on this region. So the mass here is going to be approximately rho of x, which is that linear density, times the length of this very small piece of fiber that I'm looking at, and we've called the length dx. So this is the mass of this very small piece of the fiber that we've chosen. And so what we want to do now in order to get the mass of this entire fiber is we want to add up the masses of all of these little tiny fibers that we drew here according to our partition. And when we add up a bunch of these rho of x dx's, that's exactly what it means to integrate the function rho of x. So here the total mass, I guess maybe we could call this, or we could write this in red. So the total mass is going to be equal to the integral from a to b of rho of x dx. Great, so let's maybe take a look at an example here. So we have a fiber being placed on the x-axis from x equals 0 to x equals pi over 2. X is measured in centimeters. A scanning electron microscope measures that the fiber has linear mass density equal to rho of x equals sine of x plus pi over 4. And this is measured in nanograms per centimeter. What is the mass of the fiber? Well, we just got finished saying that if we have a linear mass density function, then we want to integrate that thing. We're told that the fiber is placed on the x-axis from 0 to pi over 2. And we are looking at the density function sine of x plus pi over 4. Well, this is an easy integral for us to do. We know that this is going to be minus cosine of x plus pi over 4. If you want to use a u substitution, you could use u equals x plus pi over 4, or you could notice that if you took the derivative of this minus cosine of x plus pi over 4, the inside function here has derivative 1, so it doesn't actually produce any additional factors when taking the derivative. So we have our antiderivative of sine of x plus pi over 4 here. We want to evaluate from 0 to pi over 2. So let's see. So we're going to be looking at minus cosine of pi over 2 plus pi over 4 plus cosine of 0 plus pi over 4 is pi over 4. So let's see. So in this, in the argument for the first cosine, we have a 3 pi over 4. Cosine of 3 pi over 4 works out to be minus root 2 over 2. So with the additional negative sign out front, that's going to give me a positive root 2 over 2. Cosine of pi over 4 is root 2 over 2. And so this is all going to give us the square root of 2. Now, since this problem, it has some kind of context, we need to actually think about what the units of square root of 2 are. It certainly makes a difference if this is measured in kilograms versus micrograms. So we're going to go back and look at the units of our variables here. So the units of x, we're told, are centimeters. So if we're thinking units right now, that means that the units of x are centimeters. We also know that rho of x has units nanograms per centimeter. So if we want to think about units there, that means that the sine of x plus pi over 4 has units nanograms per centimeter. In order to get the units on the output of an integral, I know it's units of the integrand times units of the variable of integration. So here, the integrand is this sine of x plus pi over 4. The variable of integration is x, so I'm taking nanograms per centimeter and multiplying them by centimeters. Simplifying things a little bit, this is going to give us nanograms. Cool. So we have a nice way of computing the mass of, say, a really thin fiber, provided we're able to get its linear mass density equation. And getting that linear mass density function is sometimes easier than actually taking the mass. So this does have some kind of practical value. All right, I think that's where we'll leave this video for now. We'll take a look at a slightly more general version of mass density in the next type of example.